Okay, hello everybody. Thanks very much for being here. I guess I should start by thanking the organizers of GOSIM and thanking CSDN for the opportunity to be here today to tell you about what we're doing at Procero to bring and facilitate generative AI on the edge, on small edge devices, using a set of dynamic optimization approaches. Before I get deep into the presentation, let me briefly introduce myself. My name is Richard REINER. I am, I guess, what you would call a serial entrepreneur. I am an ex-developer, but I'm not allowed to write production code anymore. I do still write code for fun purposes. I've built and sold a series of companies. My first company, Assurant, is today part of Trend Micro, the Japanese cybersecurity company. My second company, Anomaly, is today part of Dell. There's another one that was sold to Synopsys, another that was sold to Trend Micro, one that was sold to Intel, and so on. Procero is one of the companies that I'm on the board of directors of today. Procero is based in Montreal, in Canada, which is, as many of you probably know, the home of Yoshua Bengio and his Mila Institute, one of the two or three most important people in the, as one of the fathers of AI, the father of deep learning, people say. I believe Dr. Bengio is now the most cited scientist of all time. And I'm happy to say that many of the people at Procero come directly out of the research programs at Mila, led by Dr. Bengio. So that's where the company emerges from. So I'll give you a brief outline of the presentation. Let me talk a little bit about Edge AI in terms of a problem statement. What is it that people like us who are working on bringing generative AI to the edge are trying to accomplish? What are our objectives? What are the factors that drive this? I'll talk a little bit about the state of the art, about the current set of technologies that people use to do that. I'll move on and talk about some dynamic approaches, which are getting closer to what Procero is doing. I'll give you a view of our solution, the Procero solution, and then since this is an open source oriented conference, I'll talk a little bit about our dual source strategy, because we are not fully an open source company, but we are committed to open sourcing some important components of what we're doing. I should say also that this presentation will be less technical than some of the presentations you've probably seen on this track. You won't see any code, but I'll try to give you an understanding of what we're doing. So, generative AI on the edge. Why would anyone want to do that when you can deploy much greater computing power with vastly greater resources in large data centers than you can on an end user's own device, on a mobile device or a laptop or even a small IoT device? Well, let's divide this into two pieces. On the one hand, generative AI deployments for both training and inference today are generally in the cloud, and I'm not going to talk about the training and fine-tuning aspects. That's just not what this presentation's about. It's not what Procero is focused on. I am going to talk about inference, so runtime, and what are the challenges around doing AI inference in the cloud. There's a list of issues here on this slide. There are issues around security. There are issues around privacy, availability, latency, energy costs, and even environmental impact. And I'll say a little bit more about each of those. So let's talk about security. There are many application domains, many entire industries that are security sensitive. Many of them are regulated. So the energy industry, telecom, of course, many aspects of government have very stringent data security regulations. The environments they operate have to meet very high standards. It's very difficult to provide cloud-based services that meet those needs. There are issues there not only about the confidentiality of data, which is usually the first thing that comes to mind when people talk about cybersecurity, keeping your secrets secret. There are concerns there about data integrity as well. So is the data that you've placed in the cloud that resides in some service or the model you've trained, are you getting access to the data that you expect to be getting access to? So there are some significant security concerns, and while there are many people who are working on addressing those in cloud-based environments, and there are many approaches that are interesting there, confidential computing, which takes the form of secure computing enclaves, so that the cloud operators do not necessarily have access to the data hosted on the servers that they're operating for you in the cloud and on the data stores. These are still very limited in their abilities. And another very viable and interesting approach is simply bring those functions to the end user's device so that there is no cloud operation involved, there is no cloud storage of data, there is no processing in the cloud, there is no data in transit. All of the security sensitive data simply resides on the end user's device. Highly desirable, difficult to do, we'll talk about it. There's another class of applications where it's very interesting to think about generative AI on the edge, and those are availability critical applications. So here we're not talking about confidentiality or data integrity, we're talking about applications that the user must have access to, or the users must have access to at all times. Interruptions can't be tolerated. That's easier to do locally than when networks are involved. That's easier to do on one device or on multiple replicated devices that are all local versus in complex cloud environments. So that's another class of issues that are helping to drive a need for generative AI on the edge. Then there's a set of issues around consumer privacy, end user privacy in general. So more and more nations, and in some cases provinces or states, have regulatory regimes around privacy. So in China, there's the PIPL, which is the privacy law. Probably the best known of all of these is the GDPR in the European Union. There's also the APPI in Japan. India has a privacy law of this kind. There isn't one at the federal level in the United States, but many states do. So California, for example, has the CCPA. In Canada, there's a law called PIPEDA, P-I-P-E-D-A. There are other national regulations. There's also a question of consumer preferences. This differs in different markets, and it's probably stronger in the West than in China or some other places. But many consumers have sensitivity around privacy, and they don't want to share more of their personal information than they have to. So it's very appealing for those reasons as well to try to bring generative AI processing onto the user's controlled edge devices as opposed to having it run in a third-party cloud. Then another class of applications that are very interesting for edge AI is anything that's latency critical. So whenever you're hosting something in the cloud, you have network latency, and that is going to impact your time to first token. You have your query that has to be transmitted, and then you have processing that takes place, obviously, and then you have a response that comes back. And the initial data for the response depends largely on, depends to a significant extent on network latency as well as on the processing speed in the cloud. And then network bandwidth, which is a different issue. And there are situations where latency is good and bandwidth is bad, and situations where bandwidth is good and latency is bad. That impacts the maximum tokens per second or the speed of transfer of your result, whether that's text or whether that's image or video. So latency critical applications also become very interesting for edge AI use cases. And then there's energy consumption, which really you can look at from two perspectives. It's about the cost of the energy, and it's also about the environmental impact of that energy use. And obviously, if we can get the same application to run on a device that operates on a power budget of a few watts or a few dozens of watts, as opposed to on large clusters consuming megawatts and gigawatts in large data centers, that's very desirable, both from a cost point of view for the energy budget and from point of view of the environmental impact. So if you think about that as a set of objectives for edge AI, we'd like to be able to deliver real-time response, so latency under 50 milliseconds, even zero network delay. We want to keep data on the device, which satisfies regulatory requirements for security and privacy. 724 availability, so that even in disconnected scenarios, whether that's loss of wireless coverage or some other kind of network interruption, those applications remain available, and then at the same time eliminate many of the costs involved in running these large models in large data centers. So a little bit of data there, very approximate, but edge compute costs can be as low as a fraction of 1 RMB per million tokens, whereas if you take the general cost on a commercial basis of running large language models in cloud environments, you're paying whole numbers of RMB per million tokens. The average may be somewhere around 10. And then, of course, you've got the environmental impact that you can save. And then finally, a really important point is the ability to scale, because if you're not limited by your centralized computing capability, the number of users who can run your application concurrently is decoupled from your capital spend. If the LLM that you've developed and deployed runs on users' edge devices, which users provide, you effectively have infinite scalability because you don't have a central resource that they're all consuming. So when you take all of those factors together, there are many people who've predicted that the adoption curve is going to look something like this, where the green line is the rather small amount of AI computation that's being performed on the edge today, and the yellow line is the much larger amount of computation being performed in the cloud. We are today on that line somewhere where they are beginning to converge, but we're far still from the crossing point. But we do think, and there are many others who think, that there will be a point at which those lines do cross, and the majority of these workloads can transition to local devices. So that is the direction of progress that we are trying to facilitate at Procero, and of course we're not the only ones doing that. So device for doing AI inference on the edge is becoming available. Current generations of processors often include dedicated AI processing units. They include NPUs alongside the GPUs, so there are now 3 processors on the die, not 2 as there used to be. Those devices are still very limited in memory and performance, especially relative to the large GPUs that are being deployed in the cloud. And in order to help close that gap and to move us along these curves, we believe that some new approaches in the software stack are needed that can help us move further along toward the adoption of edge processing for these workloads. So how have people been attacking this problem up to now? Most of the approaches that we're familiar with, that probably most people in the room are familiar with as well, have been static optimizations. They are one-time transformations at the level of the model that modify the model so as to make it lighter weight, often at the expense of some accuracy. So probably best known of all is quantization. So you take a model that originally uses large floating point numbers, you quantize it so it either uses smaller floats or maybe it uses integers, maybe it even uses small integers, 4 bits, even beyond. There have been 2-bit approaches and fractional approaches in between 1 and 2 bits. Now that necessarily comes with accuracy losses, so there's a trade-off there. And there have been various attempts to compensate for the loss of accuracy using approaches like QAT, quantization-aware training, NPTQ, post-training quantization, and a number of other things. So quantization pretty well known, pretty well understood, and we've probably reached the limits of what can be accomplished with that technique. Another approach that has come into more and more use is distillation, where effectively a larger teacher model trains a smaller student model, and the student model is what you eventually deploy. The idea being that the student model will closely approximate the performance of the teacher while occupying a smaller footprint, requiring less processing and residing in less memory. Again, there is some loss of accuracy, difficult to compensate for in these cases. More static approaches, sparsity, pruning. There are lots and lots of different approaches within that category, but they all effectively amount to an attempt to identify and to remove redundancies or less important parts of the model. You're hoping to cut out some parts of the model in the hope that you still have something functional when you're done. and again, there is often some loss of accuracy there. And then another family of approaches come under the category of optimizations to the attention mechanism. This is an area where there's actually been an awful lot of current research. So the idea here is that the attention mechanism is often one of the biggest bottlenecks in the processing of an LLM, and these approaches are trying to lighten, trying to reduce those bottlenecks to some extent. So some well-known approaches here are MQA, multi-query attention, group query attention, GQA. These are trying to reduce the size of the key value cache. You've got sliding window attention, which tries to restrict the attention mechanism to a fixed size window. There are a number of other things there. Again, still static approaches. Then, over and above what you can do statically, there's a group of very active research projects around the world which are focused on attempting to dynamically optimize over and above what can be achieved with the static one-time optimizations. So there are approaches here that focus on batching, where you're grouping multiple requests together so that they're processed in parallel. That tends to be good for throughput, but bad for latency, so there are trade-offs involved. There are various approaches that attempt to exploit parallelism, either at the tensor level, where you're splitting model layers across multiple execution units, at the pipeline level, where you're splitting the model layers vertically and dedicating an execution unit to each layer, or at the sequence level, where you're splitting the input sequence and parallelizing that way. Well, I'll say some more about parallelism approaches in a little bit. There's some interesting work that's being done around speculative decoding, where you're using a smaller, faster, or approximate or draft version model that generates a speculative response, and then you use the large model to check it before outputting it to the user. It's a really interesting area in that some of the approaches have been kind of tantalizingly interesting without actually delivering results, because the savings of the draft model are generally consumed by the larger checker model. There is some brand new work just published a month or so ago from Google that extends those approaches in a really interesting way, where you're talking about speculative cascades as opposed to the simpler approach that I've described on the slide. And that's really interesting and really promising. Then there are some other approaches that focus on dynamically managing the KV cache. So page attention does that. So it's basically a paging mechanism similar to what you get in an operating system in an operating system's virtual memory manager. And then the last bullet on this slide, which probably would be the most interesting part of this presentation if I were allowed today to say more about it. I have 10 more slides that expand on that last bullet, but I cannot present them today for a couple of reasons that I'll talk about in a minute. But there are a number of proprietary methods that we have developed within Procero. There are 6 of them and more in the lab, which extend or supplement or improve upon some of the other things that I've mentioned in the dynamic category, and that are part of the Procero platform. So I can't go into a tremendous amount of detail there, because those are the secret sauce. Those are the special IP of the company. The IP protection around them is not fully completed yet, and so I have to be very careful not to do anything that could count as disclosing that ahead of certain key dates. But I can say that those dates are coming up very soon, and we will very shortly be able to go into much more detail about that. So I apologize, but today I have to just leave that kind of opaque and say that we do have some additional methods beyond the things that are in the literature. There will be a set of publications. There will be some code shared. They are already part of our closed source platform, but we're not able to do further disclosure about them as of right now. So what is our solution? It really is kind of an all-encompassing product that includes nearly everything that I've talked about today in terms of the static and the dynamic approaches. So it is a comprehensive and unified, highly performant edge AI acceleration and optimization platform. It uses a broad array of optimizations, static approaches as well as dynamic ones. It provides broad compatibility across, I think today we have 5 families of CPUs, GPUs, and NPUs that are supported. It extends, operates effectively as a plug-in to a number of the most common runtime environments for AI inference. So we work within the context of some of the things you see listed here, and I'll go into more detail about that later. and supporting a fairly broad family of model architectures. So a number of transformer-based language and vision models, and some other non-transformer designs that are still matrix dominant, linear ops, so on, and which provides benefit even if the static model, even if the model you begin with has already been statically optimized, it's been quantized, it's been pruned, or it's been sparsity optimized, and we support those data formats directly. I'm not sure how readable that is, but kind of a high-level view of the overall architecture. So, big blocks is the Procero Edge inference engine, which is operating within the context of one of the inference products that I've talked about. There is a scheduling layer which exploits parallelism, in fact, heterogeneously across different classes of execution unit that may be present at runtime, so CPUs, NPUs, TPUs, GPUs, and even in some cases, some other kinds of dedicated hardware. There are basically two major pieces of software here, although we think of it more modularly than that, and I'll give you a further breakdown. But there is the static one-time optimizer that applies a set of static optimization techniques and transforms the model into a representation format, a data format, upon which we can perform our dynamic optimizations, where there is dynamic pruning, there's dynamic sparsity, there's context preservation, and some other optimizations. So we've tried to bring this to market in a way that's pretty highly modular. So the component we call EdgeForge is the component that's focused on parallelization and heterogeneous execution. That's capable of providing parallel execution of inference operations across homogeneous or heterogeneous hardware, so multiple CPU cores, obviously, multiple execution units within a GPU, but also heterogeneously across CPUs, GPUs, NPUs, and even in some cases, DSPs that may be present in the system. NeuroPulse is really kind of the core of all this. That's the module that performs dynamic pruning, conditional computation. The focus there is on maximizing performance and minimizing power consumption, generally in a way that is lossless with respect to accuracy. The Pathweaver component is about adaptation. So that's about selecting the optimization modes and some of the parameters of those optimizations in a way that's sensitive to the execution environment you're running on, so what might be appropriate if you have an NPU present versus if you don't, or if you have one class of GPU versus another. So those are the three components that are currently available in the market, and some parts of which we have already made available as open source contributions, and I'll talk later about where. And then finally, there's one component that hasn't shipped yet that's expected in the second quarter of next year, which is again about adaptive inference, but this time real-time adaptivity based on the nature of the query, the degree of precision that might be required, trade-offs between latency and bandwidth, what else might be executing on some of those execution units. So that's the dynamic, sort of doubly dynamic, provides dynamic optimization in a way that is dynamically sensitive to the execution context. In terms of compatibility and integration, so hardware runtimes, we're integrated with the Qualcomm AI engine, with Intel's OpenVINO toolkit. We have some pretty close collaboration with some of the companies listed here. We operate on Samsung's AI platform, on AMD's XDNA, on a variety of ARM-based platforms. Again, supporting, in most cases, all of the execution units that are present, the CPUs, the GPUs, the NPUs, and even in some cases, DSP cores. In terms of model compatibility, I don't have a list here because the list is pretty dynamic, but I believe it's 12 major families of LLMs, as well as some other models of some of the other classes are currently supported, and there are more being added. The optimizations that we're providing are not model specific. They're generally pretty highly model agnostic, although effectiveness of some things may depend on which model you're running, and so the dynamic piece, the dynamic squared piece that I mentioned, does take that into account. The use cases, I think this is fairly straightforward. So we're aiming to facilitate the use of LLMs first and foremost on mobile and on embedded devices, so to deliver high performance inference without heavy compression, without high levels of accuracy loss, and to do that in a way that's also economical in power consumption. That includes conversational AI at the edge, even on devices smaller than laptop and mobile phone classes of device. We're very interested in facilitating privacy by design, which is a movement to address privacy requirements from the beginning of the inception of a product, which is obviously much more straightforward and often much more effective if you're aiming to target the product to an edge use case as opposed to operating in the cloud. And then distributed intelligence, where we can bring much of the LLM processing, much of the GenAI inference onto what might be very small devices. There might be IoT devices scattered across a broad footprint, for example. This is starting to sound a little bit too much like marketing for this conference, so I'll go quickly on this slide. But what are the benefits? Smarter models that you can run on the same device. So you can run a larger model, you can run it faster. In terms of benchmarks, generally, there's some variability in this depending on what class of hardware we're talking about and which of the inference frameworks we're talking about and which of the models we're talking about. But as a rough rule of thumb, we're providing about a 50% benefit in the size of model you can run on a given device with a given configuration, and at the same time, roughly speaking, about a 50% benefit in performance, in throughput. That also does come with lower latency, lower time to first token. It brings with it ultra-efficient power usage, and of course, privacy is built in because we're running on the edge. Finally, talk a little bit about our dual source strategy. So some components of the stack do remain closed and probably will remain closed, but we are releasing meaningful optimizations. We've initially done that through some of our partners. So there are some components of the Procero stack that are appearing within OpenVINO. The first few have been committed, and you'll be seeing more coming, and also within the Qualcomm AI runtime. And then finally, you'll be seeing the bulk of our contributions coming on our own GitHub. You won't find much there today, but that'll be coming, some of it by the end of this quarter, and then more of it early next year. So that's it. I hope I've given you a little bit of a view of what we're trying to do at Procero. There's my contact information. If anyone's interested, I'm happy to put anyone who's interested in touch with members of the engineering team. I'm a board member at Procero. I'm not an active member of the engineering team, so my ability to answer deeply technical questions that you may ask is probably limited. But if any of you want to follow up with me through any of those contact points, email, WeChat, Telegram, other things, you can find me on LinkedIn. I'll be happy to put you in touch so that you can get all the details that we can share with you. Thank you very much.